So today I'll be talking about optimizers, which you might have heard whenever you're training a neural network or really any sort of any sort of modern machine learning, where you have to do training, even Gaussian sledding, you're going to do some sort of, you're going to use some sort of optimizer. Um, so very quick preface. This is a little bit of a warning, but most of what I'm going to talk about today is through empirical testing. So I can't prove to you easily and in a timely manner why one optimizer would be better than another. The main issues are going to be with respect to the tasks that you're accomplishing. Some optimizers are much better at certain tasks than others. The scale of the model you're training, and just the proofs are not very pretty. You're working with stochastic optimizers because typically you'll train on a subset of your training data, not all of the training data at once. That's what batching does. So this is just a little bit of a warning. Like if you're expecting something super formal about why an optimizer works better than another, that's just not the case. This is very inductive in process. Or like one of the papers say, we offer no explanation as to why this was for a different topic, but we attribute their success as all else to divine benevolence. And this isn't a very serious paper. So, but essentially the second topic is that most of these optimizers revolve around the same idea, which is it's a first order method. Most of them are not real quasi-Newtons. They don't follow some of the quasi-Newton requirements, which I talked about last week or 2 weeks ago, when I did the BFGS presentation. But essentially, a lot of the optimizers are going to be some approximation, and we can prove that there's some approximation of the diagonal of an approximation of the Hessian. So they're very loosely related to second order methods, like quasi-Newtons. But again, it's very loosely related. So we're mostly going to stay in the first order method, except for like one optimizer, which is very specifically going to touch on second order. And as always, this is a reading group. So if you don't understand something, ask. I may have made mistakes. Hopefully I didn't. Like if something is confusing to you, someone else is probably confused. All right, and let's get started. So how can we improve a model's weights? If you're training a neural net, how do you improve model weight? Anybody can shout an answer. Yes.
You just wait based on loss.
Yes. The goal is you want to accomplish some goal, so here it would be reducing loss. Can anybody think of maybe an algorithm to do that? Yes.
Gradient descent.
Gradient descent with backprop. So that's going to be the main idea, is we can use backpropagation to find gradients, and then we're going to use some update function, like gradient descent, to minimize your loss function. In this case, the goal is to minimize the loss function. And here I just included like a visual landscape. This might be like the only nice visual of today, but the idea is this is a very trivial visualization in the sense of in reality, you'll have, hundreds of thousands, millions, or billions of parameters. You can't fit it in a 2D drawing, right? You need like n dimensions for your drawing. But this is like a nice visualization, and it shows you like the lost landscape is kind of annoying to work with. It's very busy, and you have those plateaus where you quickly descend towards a much better answer, towards a much better loss. So we're going to work essentially trying to minimize those. Okay, that off. Yeah, I'm gonna keep this. I guess I'll keep both of them on the PC for now, and if there's a question, I'll be able to draw. I'm realizing that might be a better idea. So that's gonna be really the main goal of today. So just a little bit of notation. I'm just gonna keep it here, and if anyone has a question about it, we can go back to this slide. But essentially, your parameters are gonna be theta. The new parameter is going to be theta plus 1, like t plus 1. Your step size, also called learning rate, is eta, or this n symbol. If you change it during training, you might sometimes see the notation as eta t, because at each step it's going to be different. Like if you use cosine, the cosine annealing, for example, you'll have a different step size. Question mark of t, so you're going to see a lot of optimizer variables I'm going to define. They're not hyperparameters, so you might see something like v of t a lot, or m of t, or w of t. Those are going to be some variable that the optimizer uses that carries through the optimization. You're also going to see a bunch of hyperparameters, so betas, lambdas, epsilon. Those are all just going to be hyperparameters. And then obviously your loss function is this nice calligraphy L. So just a little bit of notation so we're not confused. Hopefully it should be pretty obvious through the slides what everything is, but this is just going to be to set things straight. And we're going to get started with some of the common optimizers, the ones that if you take 373, you're going to have heard about. The first one, as we mentioned, gradient descent. Why is it stochastic? Because you sometimes don't have the whole data, so you're only going to work with a subset of the data. So in that sense, because a subset is chosen randomly, you're in a stochastic world, not in a perfect gradient descent world. Very easily, you do theta minus your step size times the gradient. Go directly towards the best descent. It's pretty nice. We can actually do a little modification. So you might see this called just sine gradient descent or sine stochastic gradient descent. Instead of looking at the value of gradient descent, you're just going to look at the sign. So should you move in the positive direction or the negative direction, right? This is a little bit more simplistic. It just tells you, should you go left or should you go right, for example? And then you always use the same gradient descent step. It can make things a little easier so you don't get, if your gradient is basically 0, you don't get stuck. So the sign can help you a little bit on that. But again, none of this is going to be, I'm not going to prove any of this. You can try to read the papers. Very few papers actually prove optimizers. So yes.
Sign in what sense?
Sign as in literally the sign of the values. Like if you have a positive,
It's one value.
like you can have, just the sign is going to be positive or minus. Like you only look at the sign. Like it's +1 or -1.
But like if there's like multiple values, then it's like a vector. Then
You do it for each of the vector values. It's element-wise sign, I guess you could say.
and then there's multiple signs. Or
Yeah, so I guess the way I should put it is like, it's just going to be a clip, like, it's going to be +1 or -1 based on which one you're at for each of them. So when you update your theta, like let's say your theta was 1, 2, like the vector 1, 2, and you might have +1, -1 times your step size. So does that make sense? Just, yeah. Momentum, so we're going to use exponential moving averages a lot today, just because they're the best kind of averages to use for those types of problems. Because obviously you want to reinforce recent events and you don't really want to care about things that are too old. So as something is more and more recent, you want to update, here it's called V. So you can think of it as the velocity or the momentum. And essentially you're just going to use what are the past gradients, and let's just use them as our velocity. So if you think about it in physics, right, even if you at some point were going 50 miles an hour, but now you're going 10 miles an hour, you might still have some of that speed from before. That's the momentum here. I don't know if that makes too much sense, but essentially, yes.
Is beta closer to 0 or is it closer to 1 usually?
Well, you can write it in multiple fashions, and in this particular case, it really depends on what you're doing. I believe for this particular one, it is going to be closer to 0, because you're going to do incremental changes, but it is a hyperparameter, and for hyperparameters, you're going to need to tune them. So I can't give you an exact answer because tuning it might give you a much better result than I can tell you. So that's just the idea of momentum. One of the nice things that it accomplishes is if you're stuck in a local minima, the momentum can kick you out of it. But it also could push you into a worse local minima. So it's a double-edged sword. Nesterov accelerated gradient essentially is just momentum, but you look ahead. So instead of looking at your current gradient for updating the momentum, You're gonna say, if I continued moving in this direction, what would be the momentum? There are some nice proofs with Nesterov momentum or Nesterov accelerated gradient, which basically show that you have better convergence than just momentum. So those are like this slide might be the only one where you have really nice proofs. But Nesterov does have that nice idea of you're going to look ahead. What would the gradient be if you did go in that direction? And then use that to update your actual gradients. All right, no questions. Perfect. Now we're going to move into a little bit more of the complicated ones. So adaptive gradients. The idea is very basic. It's you want to have small updates for a gradient that you've changed a lot. But you want to have more updates for the gradient that you haven't changed a lot. I know that sounds a little weird, but essentially it's to promote the fact that the gradients that keep changing that keep changing a lot might not truly help you get to a minima, but a gradient, like a gradient direction or a parameter that does help you a lot will only change infrequently. That kind of makes sense. I know it's a little weird, but the idea is you want to change your gradient according to how much the parameter's previous gradients changed, but you don't want to just do momentum, right? You want to be a little smarter. And so here the idea is they're going to use a matrix, and we're only going to use the diagonal of that matrix, and we're going to keep track of the squares of the gradients so far. So it's just the sum of the squares and then take the root of them. Epsilon is just some tiny value to avoid dividing by 0. And so this allows you to consider like, if you've already changed, a parameter a lot, and it clearly didn't do that, like you've already done the updates. Now you can look into the other parameters. That kind of makes sense to everybody. I know it's not the best optimizer to explain. But again, I'm going to try to go through quite a few of them today. So there is also RMS prop. So instead of just doing the sum, we're going to use an exponential moving average. So very similar to momentum. But now we're going to use the square of the gradients. Again, here we have that beta term, which is a hyperparameter that we can tune to have our exponential moving average. And you're just going to plug it in. And now you have the exponential moving average of the squared gradients instead of just the sum of the squared gradients. Make sense to everybody? Like not very different from the previous one. Another one that you might have heard about a lot is Adam. So the idea of Adam is we're going to have moment estimates of the gradients. If you've not heard the term moment, essentially you can think of it as like, how do I put it? Essentially in probability, like stat 416, you'll get it taught, but like the first moment is going to be the mean. The second moment is going to be the uncentered variance, so E of x squared, like the expectation of x squared, for those of you who are in stat or who have taken it. So essentially what you're getting from the moments, mostly if they're unbiased, is going to be what is the average and like how much spread there is around that point. Those are going to be the two main points, the uncertain variance and the mean. And so that's what Adam is going to keep track of. How have you typically moved with your gradient with an exponential moving average? And what was the variance like previously? And so you want to change based on whether or not you have a high or low variance. So if you have a very big variance, then you're going to change a little bit less. That's very similar to what we had previous with RMS prop, right? It's the idea that if you keep changing in many directions, you want to have a smaller updates. But if you change rather monotonically, like you don't have too many changes, we're going to kind of go the same way. The reason why there's a little M hat and V hat is going to be a fun little exercise to the audience, but essentially you can show that by dividing by 1 minus beta t, B1, beta 1 and beta 2, you make the expectations unbiased. Essentially, like you just plug in the expectation formula for G, and you try to make them equal, and you set it as a sum, and then you simplify a little bit, and you'll see that you need that division. It really only matters when you're very close to 0. Obviously, because your B1 and B2 are always going to be less than 1. They're going to be between 0 and 1. So eventually, like, that's just going to disappear as you take enough steps. But very close to the beginning, to your first few training steps, it's going to matter a little bit. And so that's just how we make them unbiased to have the nice properties of Adam. In the sense that it's unbiased and we use moment estimates, and that's how we adapt the gradient, hence adaptive moment estimation, Adam. Make sense of everybody? No questions? All right. And also, yeah, it's because the initialization of M and V is going to be 0. That's why you're going to have a little bit of bias. I guess intuitively, your mean is almost certainly not going to be 0. But if you start your exponential moving average at 0, it's going to have an impact. And we can't really choose it to not be 0. So, yeah. Adam W, I'm not going to go through all the proofs, but for those of you who have a little bit more experience, you might know what weight decay is. The idea that over time, you'd hopefully decrease your weights a little bit. So you just don't want to have very large weights. It's the same idea as L2 regularization. Essentially, you don't want to have weights that are too big, just to make sure you don't overfit too much. And if you do stochastic gradient descent, actually L2 regularization and weight decay can be the same thing, given a very particular parameter, which is going to be your lambda divided by alpha, which alpha in this case is the step size, but I just took the screenshot of the paper. But when you try to do that with any sort of adaptive gradient method like Adam, for example, or RMS prop, that property no longer holds up. And that's the proof of proposition 2, which is, again, I'm not going to go through it perfectly because we have a limited amount of time. Like, yeah, it's already 22. So the proposition 2 is going to be essentially just telling you you can't use L2 as weight decay. And so the basic idea is going to be, let's add the weight decay back directly into what weight decay should be instead of using L2 regularization. That's kind of the main idea. Is Adam W fixes an issue when people use L2 regularization. For those of you who have more ML experience, that might make sense. For those of you who don't, that might be very confusing. So if you have a question about something that you don't understand, tell me. Yes.
Just to clarify, this might be a stupid question, but is the point of Adam W is that there is the weight decay in the L2 regularization, right?
The point of Adam W is going to be, how can we fix the fact that in Adam, if you use L2 regularization, you don't actually end up with weight decay. And you would like to have real weight decay, or at least the idea of weight decay. And so they're going to show, well, I'm going to show you, but like their entire paper is like, let's decouple the weight decay from L2 regularization and have it specifically in the optimizer. So I think this is a nice segue. So the idea here is going to be, in Adam, your weight decay, or your L2 regularization, but I'm just going to say weight decay, is essentially in your gradient. It's going to be found in your gradient. That's when you have like your loss function. And you later on feed it through the rest of your problem. So just because of when you take the derivative, that's what you end up with. Like you just end up with weight decay. That's actually kind of bad, as I mentioned. Like you can prove that this will not end up being real weight decay with Adam. And so instead, you're just going to add it directly into your weight updates. So the weight decay does not get regularized by the rest of Adam. Does that kind of make sense now? Like, you're basically shifting where the weight decay truly happens. And so now you're no longer regularizing your weight decay, so you get the true properties of weight decay, which helps you, reduce overfit. So it's a very minor modification, but it is an improvement because theoretically, that's what you should expect when you do weight decay. But the original Adam didn't take it into account. So this is just a minor modification, but most people use Adam W, so I felt like you needed to know a little bit about what was the main difference, which is just that minor modification. But since everybody pretty much uses L2 regularization, like it's pretty important. That makes sense, everybody? Like, all right. Hope you like the highlighting. That took me a surprisingly long time to figure out. Yes. Hi. Grab pizza if you want. We're kind of halfway through the presentation, but we're going to get to the newer stuff. So Lion, Muon, Sophia, that are going to be the three main optimizers that have become like pretty important since the 2020s. So Lion is kind of a fun one. Essentially, the team that came up with Lion thought about how can we determine what's the best optimizer? And the answer is not to do the work yourself. Use a genetic algorithm, so AutoML, to basically create an optimizer for you. So you train, use a classical ML approach to try to find the best optimizer possible. And so that's what they did. This is Google Brain Team. And so they created Lion, or Evolved Sign Momentum Lion. Like, yeah, I don't know why they didn't go with something simpler, but I guess ESM sounds worse. So Lion is essentially just an optimizer that was figured out by another model. So it's kind of unique in that sense. Like, there's no real justification as to why it works beyond that's what we figured out, and it works pretty well. The main thing here is you only track one variable, the momentum, the M variable, and your C variable is an extrapolation. So interpolation? I think it's interpolation here, actually. So you use your momentum to compute like your new like gradient, like effectively what your gradient should be. If we use the momentum, but it allows you to have two different hyperparameters. So the momentum can be significant, can have a lot more memory, if that makes sense. You can keep track of a much longer sequence of events, but your C can use most of the, like mostly the most recent update. So you can have like, that double idea, right? Very slow, very fast. So it gives you a little bit more information. And here the main improvement of our Adam W is going to be because you're only tracking one variable instead of two, like we were before. It's a lot faster to compute, and you obviously only have one variable, the momentum, to keep track of, so you have a lower memory footprint. The main thing here is obviously, well, there's a sign. Again, it's very similar to what I mentioned earlier on. Like, you can use the sign of your gradient updates. That typically matters a lot more than the actual values of your gradient. And again, there's the weight decay here you can find with the lambda theta t. Sometimes you might see the M update below the theta, but just for the purpose of clarity, I kept the theta update at the very end of all of my slides. But if you look at the actual paper, it will be flipped, just as a friendly heads up. Yeah, so the only thing here is you will need typically smaller learning rates because you're using the sign, so your changes are a little bit larger because of the, right, because if you have a sign, you're always going to take like the maximal size of the change. And you'll have to end up with a smaller update size, which means you need a larger weight decay, right? Because if you make n or eta smaller, then you need a larger lambda to keep your weight decay the same. And there's no extraneous hyperparameter. By that, I mean, you don't have to hyperparameter, fine tune like epsilon, right, to like 0.0001 to ensure no division by zero. On that same note, you also don't have divisions. So, divisions are potentially like one of the most inefficient parts of computer science. Now, with GPUs, it might be a little different. I don't know enough GPU kernels to speak about that. But essentially here, you're going to have much faster computation and lower memory footprint for actually an optimizer that typically works just as well, if not better than Adam. And it has a cool history. So that's kind of the memory efficient optimizer. So now we're going to talk about matrix-based. Muon is also quite unique in the sense that we're only going to look at matrix or 2D, so matrix of parameters. Those are very, very common if you're working with something like an LLM or some sort of transformer, because your attention, weight matrices are matrices, they're 2D. And so the idea of muon is we're not going to update each parameter independently. We're going to update the whole matrix at once. And they have that weird idea of the Newton-Schultz iteration, which is essentially saying we're going to try to orthogonalize the update matrix, which I know sounds a little weird, and I just put the idea of orthogonalization, which is essentially like the matrix times itself is going to be just the identity matrix, like one way or the other. And you're also going to try to like make it as close to the original matrix as possible. So you're trying to find some matrix that is orthogonalized, but also very close to the original one. So you're just trying to do that as your main idea, or semi-orthogonal, I guess, would be the better way. Their idea, and this is a speculation, again, I'm so sorry that this is, personal thing, but like, this is not provable. This is all, empirical and ideas, not necessarily provable. But the idea here is that if you have orthogonalization, you're going to look more into the rare direction of the updates. And so muon allows you to update your weight matrix in a way that might not have been so common before, or a direction in the space of your parameters that you barely updated before, and now you're going to update them a little more. Whereas the other directions which dominate, typically, if you look at the Hessian matrix or the diagonal matrix, you will see that there's a few directions that will dominate, or a few parameters that dominate, and you can look, there's directions that dominate. So this allows you to look into some direction that don't dominate quite as much. It's a little bit like the idea, with Atom or RMS prop or Attograd, where some directions you want to update more than they're actually getting updated, and some directions you want to update a little less than they're typically getting updated with gradient descent. You might think this is incredibly expensive, but it's actually not. It's less than 1% of flop, which is the computation in ML. So, and this is for LLMs, so they consider batch sizes. So the actual algorithm looks like this, where again, you have your theta, but here it's a 2D matrix of weights. It's not just a single parameter. And so you're going to keep track of that B matrix for your update, right? And you're going to update it, it's just momentum again, right? You have a B matrix, you update it over time, it's momentum. We've seen it a lot. You update it with a new gradient, you orthogonalize it, and you use that to make an update to your 2D matrix. And like typically this is actually significantly better when scaled, particularly compared to Atom. Many of the reason here is going to be, the main thing you're updating in LLMs is going to be square matrices. And so because muon focuses on square matrices as opposed to Atom, which focuses on any type of parameter, muon is a little better. And you can obviously add your weight decay, right? I hope by now that's not too surprising that weight decay is kind of everywhere. The Newton-Schultz algorithm is the way that you make it as orthogonalized as possible. In this particular case, all they're doing is they found a few sets of constants, so lowercase a, b, and c. They optimize the hell out of this algorithm to find the best constant that works, specifically when you have 5 iterations. So that's why on the previous slide, I said Newton-Schultz 5, now Newton-Schultz b of t plus some number of iterations. It's 5. And so it's 5 because they've already derived the constant. If you wanted to do a different set of constants, you would have to compute it differently. And again, it's just going to be, you're going to want to have your transport in a very specific way, and you're just going to make some updates to your matrix, which is going to be normalized. You're going to normalize the input matrix, do a bunch of updates. I'm not going to go too much into why this algorithm works, and then you return it. Basic idea is you just have to use it with 5 iterations. And so that's kind of what muon does, is it orthogonalized your update matrix, your updated momentum-based matrix, and you use that slightly more orthogonized, to update your gradients. It's not perfectly orthogonalized because we only did 5 iterations and not, infinite steps of iterations. But again, we're talking about a practical field. You're just gonna have to draw the line somewhere. Let's go, Myung. Anyone has any question about it? Yes.
Quick slide when you mentioned dominating directions.
Yes.
I'm just curious, but like, does it mean it's like the does it have any correlation with the attention scores? Like that direction have like larger number, like larger scalar number?
I don't believe so. This is just a general idea with 2D matrices of parameters. It's like,
But
sorry.
the matrix that you mentioned, is it like the attention matrix, right?
This is not the attention matrix itself. It's going to be the weights that are used to compute the attention matrix. So, like your WV, for example, like the weights for the value, like that is a 2D matrix actually. Right. So there's a lot of 2D matrix of weights. Now the attention matrix itself is actually not, it's not a parameter. It's not a bunch of parameters, but what you use to compute it is a bunch of parameters. And so this is what it's saying about is the directions that you use when you optimize those parameters. There's some directions of the weights that are dominating. If you think about, x squared plus y squared divided by 1,000, you're going to obviously optimize your x squared first. That's going to be the dominating direction. But actually, you would like to optimize both of them equally, or you would want to optimize them differently. You would want to optimize y squared with a much larger step size and x squared with just a regular step size. Because otherwise it's going to take you a very long time to optimize your y squared. That's kind of the idea here. It's like there's that rare direction, which is still very useful, but for some reason, there's a more dominating direction. That makes sense? Okay. So that's kind of it with Muon. It's actually been published in a blog more than a real research paper, so you can read the blog. All my sources are going to be at the end, and I'm going to put them in the Discord right after I'm done, so you can take a look for yourself.
Like among all the optimizers, one is like the most popular one, like recently, like I guess the whole teaming model is
I will
the whole industry is around.
tell you at the end which ones you should use, kinda. I'll tell you more about that at the end. Right now, I'm just presenting the various optimizers, just so everybody has a foundation of what they are. And, let's say you get an internship this summer, and your boss asks you, hey, what optimizer did you use to train your model? And you tell them, oh, I did gradient descent. They're going to laugh at you because you have so many other options. But if you tell them, oh, I used, Adam W, which is currently one of the big ones for classical just neural nets in general, they're going to be like, oh, okay, so you're state of the art. But then if you're able to explain why you chose it over other ones, or maybe, you say, oh, I used Lion because we have low memory, like we don't have that much memory available to us. You're not giving me much money because I'm an intern. I only have my local GPU. Then I use this to just do a proof of concept. So that's kind of the main goal right now. At the end, I will cover it when we have some time. So the next one, I guess, well, we'll have some time. The next one is going to be Sophia, which is my personal favorite because we're actually going to look at the Hessian now. Everything before, mainly Adam, you're able to make some very loose connections to the Hessian. But Sophia is actually going to really try to look at the Hessian. So the main idea here is, like I said before, we're still not going to be true quasi-Newton, but we're going to look at the diagonal of the Hessian. And the diagonal of the Hessian is going to be the second derivatives for each individual parameter. And so you can think of it as like, if you only looked at parameter, 159, what is like the second derivative? If you only looked at parameter 67, what's the derivative? See, I got some attention back. So that's going to be the main idea, but Sophia is also kind of smart. They realized, if you do it at every single step, it's going to cost you a lot of compute power. So let's just compute it every k step. Maybe every 10 gradient descent step, we're going to update our second derivatives. And this is actually quite normal. Like your second derivatives update are very, very small compared to your gradient updates. Like you don't change second derivative updates nearly as often as you change the gradient. And so they have two different ideas. I'm going to go very briefly into depth with them. So the first one is just going to be, let's just have an unbiased estimator. And so this is going to have same runtime as mini batch. It's a little bit less efficient, but it's unbiased, so that's nice. The second one, which is, you will have to read the paper to fully understand that one, but we're going to use mini batch gradients with sampling. So that one I'm not going to go nearly into as much depth because it's just a like 2-page proof with probabilities, and most people would not enjoy that, I think. But yeah, essentially your idea is your Hessian, like that's your diagonal Hessian. And you're gonna have obviously your regular momentum, right? Like everybody knows momentum by now. Do I need to re-explain it, or everybody got it? Good. So your momentum, same thing as we've seen before. Estimator, so that's going to be either A or B, one of those two algorithms. I'm going to go into a little bit more depth next slide, I think, just to give a very brief overview of what they are. And then you're again going to use, exponential moving average with them. As I said, lots of exponential moving averages today. That's only, on when you're updating them, so on case steps. Otherwise, you just keep it the same. There's a little bit of trickery, so you're going to clip it. I think it's next slide where I explain exactly what clipping is, but I'll go into a little bit more depth. But essentially, you're limiting to plus or minus rho, which is that parameter here. So you just don't want your momentum to be like too big or too small. And then you're going to use also like the maximum of the Hessian, just to get the biggest directions, like to consider like the worst, or I guess considering the best, like just the maximum, like second derivative of the diagonal of your Hessian. And again, you see that little epsilon here just to make sure you never divide by 0. And can anyone tell me what this term is? What? Weight decay, yes. As I said, we're seeing it a lot. Momentum, weight decay, they kind of show up everywhere. And we love them for it. So the first thing to say is, like, the estimators, I'm going to go there at the bottom of the slide, but they're actually not very costly. Like, it's 5% overhead. So the question is really going to be, like, is this 5% overhead every, 10 step, like, worth it? Or in this case, like, I think it's averaged 5% overhead per step. But, like, is it worth it to have that little bit of overhead? Or would you prefer to have less overhead, but you might converge in a few more steps? That's going to be a practical question. But in their tests, it was worth it. So again, you're going to clip the, so coordinate clipping is going to be like just for your momentum, just so you don't go too far in one direction or the other. So that's what I said, like you look, is Z like between, positive and negative rho, and if not, you go into whichever rho is the one. So, if Z was like negative 1,000, but rho was 1, you're just going to have negative 1, because minimum of negative 1,000 and 1, negative 1,000, maximum between negative 1,000 and negative 1 is negative 1, exactly. So the second thing is just with this max term here, again, you have a hyperparameter, but essentially the second idea is when your Hessian is negative, you just become sine gradient descent. Because now you're just going to divide by epsilon, so you actually stop caring about this. And so now you're just having a clip, which if you set it to, a particular constant, like is essentially, if you set like that constant to be, I believe, 0, then you're just going to end up with sine GD. Well, sine GD with momentum, if depending on how you do it, but yeah, like it's sine GD and you have momentum, not just the raw gradient, but essentially Sophia makes sure that if you have a bad Hessian, you go towards a very trustworthy optimizer. Like and a beta Hessian is a negative Hessian. Because a negative Hessian means that you're pointing, like, you know, you have that shape, like, I don't know if, how to explain, like that, yeah, that concave shape, like in the second derivative. So you're going to look at a maximum instead of a minimum. And I don't know about you, but I like to go towards the minima of my loss, not the maxima. So, you know, you can judge for yourself, but I would hope that we can all agree that we don't want negative Hessian values. There are two estimators. So the first one is the unbiased estimator. Essentially, you're just going to draw a few directions from the spherical Gaussian. Essentially, draw a few random directions. Use use this function. What this actually is the Hessian Hessian vector product. This is actually very easy to compute. It sounds like you might think, huh, I have to compute the secondary. Actually, this is very quick to compute in PyTorch or JAX. Like there's a very simple trick to do it. So you just do it a few times with vector u, which is, you know, a random direction. And because you have an unbiased estimate, because this is, you know, if you run this in your estimation function, it's unbiased. Pretty nice, pretty trivial. Second one, so it's again that idea of the Gauss-Newton decomposition, which I'm not going to go into too much depth, but essentially you're going to use a bunch of mini batches, so XYs. You're going to use them to compute the logits, and like then you're going to use those logits for your loss or the gradient, and then you're going to use those gradients essentially dot producted with themselves to get the final Hessian estimation, where B is just going to be, I believe it's not on there, but it is like it is just a scale. Oh, this is the number of batches you're going to pick times the gradient squared. This makes sense if you read through the entire proof. Again, for time's sake, I'm just not, it's not that important unless you want to re-implement Sophia from scratch, but there's already Sophia implementations for PyTorch. Both of these are pretty good. Obviously, Hutchinson's is so much easier to implement and like to derive, and it is unbiased. But GNB works slightly better in practice. Even though it is biased, the Gauss-Newton decomposition is actually a little bit more correct for your Hessian. It's closer to your Hessian. So the diagonal of the GN decomposition, or Gaussian Newton Bartlett, eventually they add the Bartlett term, that's going to be a little closer than Hutchinson, but in practice, they're actually pretty much the same, like very minor difference. You know, it's just like if you want that tiny bit more efficiency at the cost of having even less legible code. So it's kind of it, Sophia. Does anyone have like a question, or like you're super confused or something like that? I don't see any hands up, so all right, no hands up. Yeah. All right, so let's talk a little bit about optimizers for LLMs and just like empirical testing. Reason why I'm going to talk about LLM specifically is because a lot of these optimizers, Lion, Muon, and Sophia, were particularly made for LLMs, for large scale models. As it turns out, you know, if you have a small model, you don't really care nearly as much about your optimizer. Like you can even, if you're only working with like 10,000 steps, you might even be able to use like just quasi-Newton, BFGS, or, you know, some other optimizer. But here, when you're looking with billions of parameters, a little harder. Yeah, they're all kind of the same. That's empirically, if you look at the same number of steps, everything that's not stochastic gradient descent is reasonably similar. The layers where you have true improvement in LLMs, and so this is particularly with LLMs, but obviously that's the area of interest, is going to be the very last layer of your layer norms in the transformer architecture. So what you could do is use, you know, stochastic gradient descent for every other layer. And then just for those particular one, use Atom or Atom W. What they did find is also you could use a muon just, you know, like if you really truly wanted the optimal, you use muon for your matrices and you use like Lion for the rest. But realistically, the recommendation of that particular paper, which is in my sources, was just to use whatever is most practical. So uses, less compute power, is computed faster. They didn't check the, clock computation, so maybe something takes 50% longer to compute. At this one, you would just need to test it out yourself on your hardware, but this is not really because of your algorithm, but it's because, the hardware, how it works with that particular algorithm and the particular computation. So kind of what you should remember from today is like the main idea is you should really just pick whatever is most practical, lowest memory utilization, fastest to run on your particular hardware. There is a really cool paper called Fantastic Pre-Training Optimizers and Where to Find Them, which essentially tries out all of the optimizers I talked about and more, and essentially shows that a lot of them aren't nearly as good as the paper tries, like their own paper tried to sell them. So most papers will essentially cherry pick a result. And so Fantastic Pre-Training Optimizer, which is a paper from Stanford, goes through, tests them all at scale. It shows like one of the main things that you might see is optimizers tend to work really well early in the training. So if you only do so many steps, you can show, oh, my optimizer is really good. But actually, later on, it evens out. They become essentially the same thing after enough steps. Same thing with scalability. So a lot of models that you might think scale well, actually, the benefit of that new optimizer decreases as you increase the scale, so the number of parameters. I know that's a bit disappointing, but that is just an empirical test. Obviously, using task-specific optimizers, like if you're exclusively working on matrices, then Muon might make more sense. And obviously, you should run your own tests for your own task. But that's kind of the main thing. I know, not super positive end note, but it is a reading groups. But at least now you know all the optimizers, why they work to some extent, how they derive them. And yeah, questions? Sorry to end on such a pessimistic note. Note. Yeah. And so my source is I'll upload the slides and yeah, grab pizza if you haven't.